Welcome, everyone. I'm really glad you all came the Friday right before reading week. We are so happy to have Georgia Roberts back. We were trying to figure out before when you came. You were here already
Once.
At least within the last 5 years. So welcome back, Georgia. She's a methodologist from StatsCan. She knows everything you need to know about methodology, so hopefully she'll be able to answer all our questions, of which we have a few.
Thanks, Kathy. Kathy didn't tell you, we used to live on the same street, so I knew her long before she was the academic director here. So we got caught up after lunch about what's her little sister doing and what my kids are doing. It was very nice. I'm so happy to be here. Anyway, hopefully the title of my talk isn't too misleading. This is more a why talk than a how talk, and I hope that's what you're expecting. I'd really be interested to know why some of you came to this. Like, what drew you? Are some of you doing projects in the RDC, or can anyone tell? Yeah, sure. Do you want to?
I've used the ethnic diversity survey, and I've tried my very best to understand weighting and bootstrap weights and everything. And I sort of think kind of I understand it, but not. I wouldn't want to, go boring and say it, right?
Okay, great. Gustav, why are you here?
Because of you. I'm also working in the RDC. I'm working in two of them right now. And I'm using census data. And I'm also using, or I will be using longitudinal survey measurements to see what it can do.
Yeah.
And trying to explore the potential of these data sets.
Great. Anyone else want to tell me? And no? Anyway, we'll leave it there. Well, as Kathy told you, I'm from Statistics Canada. I'm actually from a very small group called the Data Analysis Resource Center. And we're in methodology. And we say that our mission is really to encourage, to suggest, and to provide good analytical methods and tools that you can use with StatCan data. And we tend to do this. We do a fair amount of consulting. We do some collaborating with researchers as well. We do some teaching. We have some courses there, seminars like this. And actually, we do a lot of research ourselves, because I don't think people realize that the way to analyze survey data is not cut and dried. The questions we get from analysts and the type of data that we are producing get more complex all the time. So we have to research. In fact, right now, our group is very small because we have 3 people away, one of whom is working at the United Nations temporarily on a big project, one who's doing a postdoc at Duke University where he's looking at some longitudinal methods, and we've got one person who's part-time right now because she's doing her PhD in some meta-analysis topics for survey data. So you can see that we're always trying to improve what we can tell people. So let's go on here. So what I want to do today is just give a few things to you. Just give you a taste of the types of analysis that can be done with survey data. Tell a little bit about how survey data are different from other sources of data. Something about the consequences of using the standard methods that you learned when you were in your statistics course at university. And then I'm going to talk a fair amount about a design-based approach to many analyses, which is something that we strongly suggest you consider. And then I'm going to just take a little wee bit of time to talk about the software that's available now specifically for survey data analysis. So, what is data analysis? I think it's actually a whole process. And in this process, what you're trying to do is develop answers to questions through examination and interpretation of data. So, as you know, you're going to go through various steps. You're going to have to identify an issue you want to study. You want to ask some meaningful questions about that. And then you want to develop answers to those questions through examining your data. And then usually you're going to communicate your message by perhaps an analytical paper. Well, today really what I'm talking about is this third step. How are you going to develop your answers through examination, specifically of survey data? So what I'm going to do is I'm going to try to break the types of analysis that you can do into two big categories, just for ease of talking about a few things. And first of all, one group would be what we'll call the descriptive analysis. And what we mean by descriptive analysis is the population about which the researcher wishes to make conclusions is finite. And this is what the population about which the researcher wishes to make conclusions, that's what I'm going to call the researcher's target population. So for descriptive analysis, it's finite, and the quantities of interest to the researcher are characteristics of that finite population. So for example, you may want to estimate the number of people in the population that have a characteristic, or the proportion of the population that has a characteristic, or the average of something in that finite population. So this is what we call descriptive analysis. So here are a couple of questions, the type of questions that would lead you to a descriptive analysis, like what was the mean family income in the province of Ontario in 2008? You can see you've got a finite population. It's families in Ontario in 2008, and a descriptive quantity you're interested in. Or secondly, were the unemployment rates in Canada the same in December 2007 and December 2010? Here we've got two finite populations, people in Canada, December 2007, people in Canada, December 2010, and a descriptive quantity that you want to compare between the two. Something that people sometimes forget about when they're talking, what's my target population? I always think you have to remember there's a time component there too, which a lot of people forget about. So you don't have a finite population if you ask for the mean family income in Ontario. What exactly does that mean? You need some time component as well. Now the other type of analysis I'm going to call a relational analysis, or you might call it an analytic study. And for this type of analysis, what the objective is to draw conclusions that are thought to have a wide generalizability. And for this type of analysis, you're usually thinking of a model. And what you're often interested in are related to the coefficients of that model. And what we usually do, if you think about it, you're usually thinking that the model is going to hold beyond the finite population that you're actually studying, where it's from that finite population that you have your sample data. So what we often say is that the researcher's target population is infinite. It's beyond that finite. You may not want to put geographic boundaries on it, or you may not want to put definite time boundaries on it. So it's probably not actually infinite, but much bigger than just a finite set of people or units at one point in time. So here are the types of questions that you might be looking at if you were doing a relational analysis. What are some of the risk factors that contribute to the odds of a person having diabetes? You would think that those risk factors aren't fixed at any point in time, and probably not even within one finite population. Or does having a university degree tend to be related to a higher chance of being employed than having a college certificate? Again, you're not really fixing place or time when you ask those sorts of questions. So I must tell you, I just dropped these slides into the StatCan template, which I was required to use, and I forgot to look at what the colors might be that were coming up. So these are a little different colors than I maybe would have chosen. So what we have here, we have a sample. That sample was taken from a finite population. Now, if you were doing a descriptive analysis, there's some characteristic, we'll call it theta sub p, of that finite target population that you're interested in, and you are going to use the sample to estimate it. maybe theta hat. But it could be that this finite target population is actually embedded within what we might call an infinite target population, which you would describe by a model. And there's something in that infinite target population that you're interested in, which we'll call theta sub xi. Now, you can see that since your finite target population is embedded within this infinite one, you probably will feel that there's a whole lot about that model that actually holds true in your finite target population. So you'd think that if you actually could study the whole finite target population, you could get a good estimate of this thing from this quantity here. But we already know that you can get a good estimate of this thing from our sample. So here are the different, you can see that there's a relationship from your sample to a finite target population to an infinite target population. And you want to make use of those relationships when you actually carry out your data, or your data analysis, because all you've got is your sample. Interrupt me at any time if you have questions or comments on this. Okay. So, what other things could we say about these two types of analysis? Well, a researcher doesn't usually just stick to a descriptive analysis or a relational analysis. He usually has both in the same research paper. He often starts out with describing perhaps the population from which his sample came, and then goes into what he's actually wanting to study. But what's important, and I indicated in that graph, is that the same survey data may be used when the researcher's target population is finite and when it's infinite. So you can, with the same survey data, you can do finite things, descriptive things, and you can do relational studies. But another thing is that the survey data provider, where here we're talking about StatCan, it usually has a particular finite target population, or several finite target populations in mind when it prepares the data files from a survey. And that's important because how the data get prepared may have an impact on how you have to study it, or it may require, if your target population, particularly if it's infinite, isn't the same as StatCan's, which it won't be if it's infinite, you have to think, are those data appropriate? Or if they are appropriate, do I have to massage the data, put it in a different order in order to carry out the analysis that I actually want to do? Now, I think most of you would know this, that if you were actually using data from a StatCan survey, we have on the StatCan website a place where you can go and get metadata about any of our surveys. It's actually, if you can drill down through that sidebar that says for analysts and researchers, get down to where data sources. And when you do that, if you pick a particular survey, practically the very first thing they always say about that survey is the target population is such and such. This is what their finite target population is. So what I did is I went onto that metadatabase and I picked this particular description up for the 2006 Aboriginal People Survey. And it says there the target population includes all people living in Canada. I've put in in 2006 because they don't really say that as part of their description, but it should be there. So all people living in Canada who have North American, Indian, Métis, and Inuit identity or ancestry. They're aged 6 to 14 and 15 years and over, and excludes people and it also excludes people living in institutions. So it tells you who exactly is in the finite population, and also tells you who isn't. And both of those you have to be careful of when you're doing your analysis, to make sure that who isn't there isn't someone you thought was there. So that was fairly straightforward. Now, some of the StatCan finite target populations aren't quite as straightforward, and the definitions aren't as well. Sometimes you're going to have to dig a little bit deeper amongst the documentation you have. For example, here we have the Survey of Labor and Income Dynamics, which is we call SLID. And it's actually a repeated panel survey. And so really, it's made up of several different surveys. Each of one is a panel. And what we do is, say for the first panel, a sample was selected from the 1993 population, and then those people were followed for 6 years. Then 3 years later, a sample was taken from 1996 population, and those folks were followed for 6 years, and so on. So each of these panels actually has a different target population. Now, I'm looking at SLID here as if you're going to be looking at it longitudinally. They also do some cross-sectional work with these data, because what they also do is for these longitudinal individuals, they also pick up every year information about the people who are living in the same household. And so they feel that they can also tell you something cross-sectionally each year. But for these this longitudinally, you've got this. Here's a different one, the target population for the 2006 census. Now, the finite target population for StatCan I'm talking about here really depends on the question that you're looking at. The target population for questions on age, sex, marital status, mother tongue, relation to person one, is actually 100% of the Canadian population at the time of the census. I put the definition of what we mean down here. And that will actually be the same for the 2011 census. But if we go back to the 2006 again, the bulk of the census information for 2006, part of the Canadian population is omitted, such as people in institutional collectives. So, for example, perhaps the 2006 census wouldn't be a good data source if what you were interested in was studying seniors, because you would be missing all seniors that were in care homes, and actually a whole lot that were in seniors' residences, because they are often the enumerators didn't know what to call them, so they called them an institutional collective. Anyway, so these are the things you have to be careful about. So now, given those examples, why wouldn't you apply standard analytic procedures to survey data, like those ones you learned in your statistics course? Well, actually, most analytic procedures in standard software assume a model, either explicitly or often implicitly. For example, if you were doing a linear regression with some of those analytic procedures, they're assuming that you've got independent, identically distributed observations. And maybe they don't put that forth so much because they think everyone knows what assumptions are behind linear regression. But most sampling strategies that we use for surveys actually yield observations that don't have that distribution. So they're different from the observations that are in your assumed model. And that's why you have to consider whether or not standard analytic procedures can be followed. So I'm just going to take a very few minutes and tell about some of the aspects of our surveys that do have an impact on the analytical results. And the very first one is the stratification. For practically every survey that is done at StatCan and elsewhere, we start out by stratifying the target population. And what we do is the population is divided into mutually exclusive and exhaustive subpopulations. Each of those subpopulations is a stratum, and then we take an independent sample from each stratum. Now, for social surveys, the strata are generally geographic. But if you're doing a business survey, the strata are often a combination of geography, size of business, and area of specialization of the business. So, but in any case, a unit that you're going to study is in one and only one of those separate pieces. And now why we do stratification is because we take an independent sample in each piece, we can assure a minimum sample size from every one of our pieces. What else can we do? We can actually use a different, as I said, a different survey design in each. And that may be important, say, for certain geographic areas of Canada. So say for Canada, practically every social survey, and practically every survey, there's at least a stratification by province. And that would say allow us to be sure we get a certain sample size from Prince Edward Island, which we wouldn't get if we were doing a simple random sample of the whole population. If stratification is done efficiently, it could improve the variance of our estimates. That's done mostly for business surveys, this efficiency, less for social surveys because most of our social surveys are so multi-purpose that we can't stratify thinking of efficiency for a whole range of variables. The next thing we do is we choose clusters. So by that I mean the ultimate units that you're interested in, and say we'll take a social survey where the ultimate unit is a person, they're actually drawn into the sample through the selection of larger units that contain them. For example, you may draw individuals into a sample by picking households, or you may pick blocks city blocks in a survey, and those would be your clusters. Now, choosing clusters, we really do it for cost saving. Most of our surveys require a frame from which to choose our units or at any level of the survey design, and it's cheaper to have a list of households rather than a list of individuals. So it's cheaper to keep up a household frame than it would be to keep up an individual frame. And it can also be cost saving for some designs, particularly say if it was a face-to-face type interviewing, to have people that you're going to actually interview be in close proximity to each other. That can save time too, time and money. But the consequences of picking clusters is that we are actually getting less information than if we picked a simple random sample of the same size, because the units in our clusters are often correlated with each other for particular variables that you might be studying. For example, education. In a household, you often will have people that are similarly educated. So this is a downfall. You get less information, and thus you get your variances of your estimates are higher than if you'd actually taken a simple random sample. Another aspect is our unequal selection probabilities, and that's particularly due to having differential sampling rates. For example, as I mentioned before, Prince Edward Island, you're more likely to be in the sample than if you're a person from Ontario, and that gives you an unequal selection probability. More for business surveys, which I don't think there are much in the RDCs at this time. You can have a real high probability to larger or more important units. In fact, we have these take-all units. They're going to be in the sample with probability 1. Or we have these, perhaps some strata where it's take none, so the probability of them being selected is 0. For social surveys, it's somewhere in between. And so the main consequence of this is that the distribution of your units in your sample is different from in the population. And if you don't take that into account, you can get biased estimates, depending on what it is you're studying. Now, we don't usually just do stratification or just do unequal selection or do clustering. We generally do them all, and we often take our samples in many different stages, so the clustering is in many different stages. So the sample we get looks very much different from a simple random sample. And what that then means is that our sample doesn't look anything like the population that we want to study based on that sample. So what that means is if you use those standard analytic procedures that you get in SAS or SPSS that aren't properly accounting for the aspects of the design, you could get poor estimates of your quantities of interest. You could get poor estimates of variability and of things that are related to variability, such as your standard errors, your p-values, your test statistics, your confidence intervals. And so what could happen is that you make misleading conclusions from the fact because you haven't accounted for the survey design. I keep saying may because it's not always the case. Depends on what you're studying. So now let's just go back to what we were thinking about your statistics course again. And you can remember back then when you were talking about statistical inference, you were talking about, you know what you observed, you only have one sample, but what you're always thinking about is what you might have observed. And that actually influences how you carry out your analysis in your tests and your estimations of variability. And if you recall, what you were really interested in was the distribution of those estimates that you're interested in under some sort of random repetition. And even though you don't have those random repetitions, you've only got one sample, and it could be that the distribution of those estimates is affected by the sample design. So here are two randomizations that I think probably are applicable for survey data you might be thinking about. This is what we call a design-based randomization, and it's probably what you would think about would be reasonable if you're interested in descriptive quantities. We've got the finite target population. You've got some sort of sampling process from it, and that sampling process could give you a number of different samples. So maybe it could give you this sample, sample number 1, and if you use that sample to estimate the quantity you're interested in, you'd get theta hat 1. Or maybe the sampling process gave you this sample, and you'd then get an estimate of this quantity from that, or this one or this one. But here's the sample you actually got, sample number I, and here's the estimate you made from it, theta hat I. Well, in a design-based randomization, what you're interested in is the variability in these things. So all you're picking up is the variability in these things depending on which sample you got from the sampling process. So you're using the same sampling design. Once you pick your data, you do the same thing about non-response. You do everything the same. That's the variability. This is probably something, if you were looking at a model, that you'd be more interested in. Now we have an infinite target population, and that's where you have your model. You feel it fits this target population. And there's a possibility that you could have different finite populations from that. The one that we actually got is this one here. And then from that finite population, there were a possibility of different samples. Here's the one you actually got. But you might have gotten this finite target population, or this one, or this one. And again, you could have then from that done sampling here. So what we're thinking about is that we've got finite populations generated from the infinite population. And when we want to look at our randomization, we probably want to include the randomness in the choice of the finite population, and then the randomness in the choice of the samples from that. And that seems like a reasonable thing that you'd want to do with survey data when you're fitting a model. But now let's think about what are the approaches that people take to analyze survey data. Well, we do have a design-based approach, and this is actually the approach that's well-established, commonly used for estimating finite population quantities when we have a large-scale survey. And then we have a model-based approach. So by a model-based approach, this is something closer to what you would have seen in your statistics courses. You're really using your classical non-survey approaches to fit your model, estimate your variances, make your inferences. But what you have to be sure of is that your model's right. And so what you want to do, the model for your infinite population should be modified when necessary so that it actually reflects the samples that you draw from it. This is the step that if you wish to take a model-based approach, this is something you have to be aware of. But once you've got your model, you can then use your classical methods. On the other hand, your design-based approach, you're going to use survey weighting to produce your point estimates of quantities of interest. You're going to use more information about the design to estimate how variable the estimates are. If different samples were selected from the same design, and as I showed you in the picture before, that's what we call design-based variance estimation. So we're only going to pick up the variability from the finite sample to the finite population to the samples, not that extra amount of variability. And then you use your design-based point and variance estimates in your analytical activities. So you'd create diagnostics using them, test hypotheses, calculate your confidence intervals. Very similar to what you would do in your classical statistics. Now, as I said, probably if you were fitting a model, that model design variability seemed to be what you'd like to actually be picking up rather than just the variability due to the design. But what we've been able to prove is that a design-based approach actually gives valid inferences for a model, for the model parameters, in most cases. And what's nice about the design-based approach rather than the model-based approach is analysts may not know enough about the design to model its impact. Particularly, I think this is actually a whole lot more true now that we have research data centers where the people analyzing the data are farther away from the data producers. And I think probably Gustav could tell us or even confirm that, say within StatCan, if you were a data producer for a certain survey in the past, you probably knew more about it, which you could include in a model if you were an analyst as well. But when we get farther away, analysts don't know enough about the design. And even if they did, we often don't put suitable design variables on our data files that a researcher could put into his model. So, and also analysts may not want them there because it changes the meaning of your model. So it seems as if a design-based approach is something that would be very realistic to use. Because, as I say, in many cases, it does give valid inferences. Here's a table actually that my colleague David Binder put together, where he said, if the people in the course go away with anything, this is what they should remember. So what he was saying, okay, suppose we look at a model-based estimator versus a design-based estimator under two different situations. The first one is we assume the model is valid, and I say, and sampling is not informative. What I'm meaning by that is the model is valid for the infinite population, and it also is valid for the sample. Second possibility is the assumed model is misspecified, or the sampling is informative. It could be the model is properly specified for the infinite population, but it isn't for the sample. Well, if you take here, let's assume the model is valid, sampling non-informative. You look at a model-based estimator. Well, you really can't do better. You're going to get unbiased estimates for for large samples. It's going to be an efficient method. You're going to get valid variance estimates. You're going to make valid inferences. So this is probably the best you could do. But suppose instead you used a model-based estimator, but your model was misspecified. Well, what happens is your estimates may be biased even if you have a large sample. The variance estimates may be invalid, and your inferences then could be invalid. So that doesn't seem to be a good choice. Now, if you have a design-based estimator, assumed model is valid. You again get unbiased for large sample, unbiased estimates. It may be less efficient than this particular situation. You still get valid variance estimates, though, and you still make valid inferences. So the main problem with it is it could be inefficient. But now look at the case of the design-based estimator and model misspecified. Well, at least we hope that you get the mean part of your model correct. We'll at least assume that and assume that where the misspecification could be in the error structure. So if the model means are correctly specified, even though the error structure isn't, and you've got a large sample, you're still going to get approximately unbiased point estimates. You're going to have valid variance estimates. You're going to make valid inferences. So it looks as if this is a good possibility for most situations. You're never sure whether your model is completely specified correctly. This accounts for that, as long as you've got the mean part of your model right. So perhaps you could take a design-based approach in most situations. And that's what we recommend, that people consider that. But right away, I go the other side and say, but we still could have situations where we found where a design-based approach can be problematic. And two of those cases are where we have a non-negligible sampling fraction or small sample sizes. Because the theory about a design-based approach giving you good estimates is these are asymptotic results that don't tend to hold under these two situations. Another situation is where models include random effects, such as if you're interested in hierarchical models or mixed models or growth models. Here, the problem is that we haven't got our methodology clearly developed yet at this point. The design-based approach has to be modified a little bit. It looks as if for most of those, you have to have sampling weights at the different levels of the hierarchy of your model. And we don't, at this point in time, put those out for most surveys. There's the occasional survey, the WES survey, which actually had 2 levels. But generally, we don't do that. And there were other problems with the results, particularly if you have small sizes of samples within your clusters of your hierarchy. But there's been some recent results lately, and we're hoping that we can get some better results in the future. Population-based case control studies. Design-based approach is fine. Everything's valid. The main problem is that efficiency is low. There are other things you could do. And then event history analysis, we still need more work here. And the problem here is often with the event history analysis, you're using data that are picked up at more than one time point. And so you're getting the lengths of your events are based on data from more than one data collection. And that combined with non-response is really, at this point, difficult. But there are people that are researching that. So it could be that in the future we can say, we can give you a design-based approach for that too, and we'll feel happy about it. Yeah.
What did you mean by case control study?
This is the type of study that's often done in the medical area, where what they'll do is they're looking at a disease, they'll take a number of people that are diseased and another sample of people that are not diseased, and then they collect information on the risk factors from, it's retrospective, But often in some of these studies, what they'll do is they'll take every case they can get and a sample of controls. And just a straightforward design-based approach doesn't give you very good, very efficient estimates.
So, but that doesn't really, that wouldn't be like one of the social surveys that we would look at?
No, we don't seem to we don't really have any case controls. There are other countries, perhaps in the United States, that would do more of that type of survey, a case control type survey. Yeah.
What about the health measures survey?
No. Again, it's an observational study at this point in time. Yeah.
Would drug studies fit into that model?
Possibly.
People that are taking placebos and people that are taking...
Yeah, if you've got something like that, yes. And I'm just trying to think of whether we could even think of some of our two-phase studies, whether we could be more efficient, where even some of our post-censal surveys, say our Aboriginal, where we use something in, say, a census to identify whether someone is perhaps Aboriginal or not, and then we take a sample of Aboriginals and a sample not. I'm not, that's not a true case control, but there could be some that you could improve on the usual design-based methods with that. But let's say we're in a situation where we actually want to do a design-based analysis. How are you going to get started? Well, the first thing you want to do is probably identify the appropriate survey weights for your analysis. I'm meaning you've designed on the questions you want, and you know that the data exists, but now you want to actually do your analysis. So you want to identify your appropriate survey weight or weights for your analysis. Something else you have to do, we want to do design-based variance estimation. So you know that you need more than just weights for that. So you have to find out what is the design information that goes along with the survey for variance estimation. It could be, just lost my, okay. In the past, you might have just had stratum and cluster identifiers on your file. Now you're more likely to have something like bootstrap weights or jackknife weights. You really should go into the user guide, any recommendations about how to use the information, and then identify suitable software. And what I mean by suitable, it has to do the types of analysis that you want to do. It has to be able to take the particular approach to variance estimation that you need to take because of the additional information. And something else that's you can actually now consider is pick something that takes into account your personal style of doing analysis. I must say, back a few years, any software for survey data analysis was clunky and hard to use. That's not the case anymore. Here's Gustav smiling, he knows that. But now you can actually often pick something that suits your style of doing analysis, which is great. So, as I said, first of all, you have to get your survey weights, pick your weights. The main reason we have survey weights there is to account for the unequal selection probabilities. But we actually do some other weight adjustments that may help to account for unit non-response, under coverage, over coverage, some auxiliary information we might have about the population, and we can include those as weight adjustments. And if you've got appropriate weighting, that's going to reduce your estimation bias for your, what we call your first order statistics, you know, your means, your ratios, your model coefficients. Here's a question that actually, Kathy, but if you're actually using something like the NLSCY, though, you go in there and you've got all sorts of weights, and you think, what is the appropriate weight that I should be using? Well, let's take the case where we just have one panel that you're following over time. So you're actually going to look at that panel at several different cycles. At the first time, here's the population, and that's the time at which you pick your sample, and there it is. By the time you get to cycle 2, your population has aged a little bit, and you probably don't have your full sample anymore because you've got non-respondents. But you still want to use that sample that you do have to talk about that original population that is now aged, what it's like now. Go on to another cycle. We've got more aging in our population, and we've also got only a part of this sample to talk about it. But we want to use this sample to tell us about that whole population. So what we try to do at StatCan is to provide some different weights so that you can use these different subsamples to talk about the population. And now, if you're using data from this particular time point, you're probably going to use the weight that weights all these folks with a positive weight and doesn't leave anyone out because the weight's 0, because you've got information from all of them. If you're using information from here, you're probably wanting to use a weight that is positive for all these folks and be 0 for the folks that have dropped out in between, and the same. But we adjust the weights as best we can so that you can still talk about this population with this subsample.
Georgia,
Yes?
before you leave that point, you used an example where it's sequential.
Mm-hmm.
But when you have something like SLID, where you have overlapping
Yeah.
panels,
Yes.
and if people want to pool data across panels,
Yeah.
what happens to the weights then?
Okay. It's, could we come back to that question? Or, yeah.
Yeah, why wouldn't you do imputation there? Like, why would you use weights and not like do imputation to like get the same amount of cases in each subsample?
Well, we've chosen that if the person doesn't respond at all, we generally use weight adjustments rather than imputation. There is that extra choice. Now, there's the occasional survey that does use some imputation for unit non-response. Business surveys often do that because, and how they'll often do it is the same businesses will be selected in the sample over cycles, and so they'll use the most recent data they got from that guy and plunk it in, and that's how they'll do it. But for most of our social surveys, for unit non-response, that's they don't respond at all, we adjust through these weights. And we'll set to 0, say, where have we got here? For here, we'll set to 0 the weights of anyone from here who doesn't respond here. And then we do some extra adjustments so that this sample, what we've got left, can still give us reasonable estimates. I'm saying we try, and it's we may not do the best job for any particular situation, but it's reasonable for a lot. So I'm just going to say which weight and thus which subsample to use may not be clear. There's often a trade-off between different possibilities, between possible bias, between sample size, because if, for example, if you decide I'm only going to use the folks that responded in that 3rd cycle, well, I'm down to a smaller sample, and I have data at earlier times on other folks, and if I wanted to use that earlier data as well as the data from cycle 3, I can't because their weight is 0. They'll be weighted out. So there's often, there's some trade-offs, and it depends on the particular situation that you're working with. Gustav, can I come back to yours in a minute? We'll go back to that picture and I'll show you. Okay. More to answer your question. Weight adjustments are generally done in an attempt to account for unit non-response, but if we have variable or item non-response, like people don't, they respond partially, but they don't give answers to every question, we usually don't address this through weighting. And surveys tend to vary on how they accommodate for that. Often they'll leave the variable blank and say, they just may say non-respond. Sometimes they'll give a little bit more. Let's say refuse to answer that question, or rather than they just didn't respond. But it's often left blank. And in some cases we do impute for that. Particularly they will impute for income variables. It seems to be done fairly frequently. Now,
Georgia,
yes.
on that particular point, because there's been quite a lot of debate about whether how you can make adjustments and whether or not you should have to make adjustments.
Yeah.
So one of the research recommendations was still looking at StatCan as part of those discussions. And one of the conclusions that we came to was sometimes it's better to just leave it, either leave it blank or indicate why there was no response for this particular item, and leave it up to the researcher to come up with.
Yeah. Yeah. And part of it is we don't really have research on how to deal with non-response is really a hot topic among statisticians. And so I think over time it'll improve, but right now in many cases we feel it's just better to leave things blank and let the researcher deal with it. Just want to mention survey weights are different from other weights. If you go into the statistical literature, or if you go looking at some of the software, they'll talk about frequency weights, analytic weights, importance weights. Well, survey weights are different, and thus they do need to be used differently. Yep.
So in the case, I'm thinking of a few situations, and we talked about one of these over lunch, where something changes drastically when you weight
Yeah.
or not weight something. Your
Yes.
findings change
Yeah.
significantly. And I keep wondering, is there some really interesting information in there that can be backed out when you see this difference? Like, can you back out that this difference in weighting actually is caused by any aspect of survey design? Like, is there anything interesting that can be done when you see the big difference to really say something interesting?
It's possible. Like usually there's you're doing weighting or not weighting. Well, often between weighting or not weighting, it could be due to the fact that your sample doesn't match your population with respect to different components. Like say for Prince Edward Island, in a sample from Canada, the proportion of PEI people that we have in a Canadian sample is much higher than the proportion of PEI people in the whole population. So if PEI tended to be different from the rest of the country in whatever you were studying, whether you weighted or didn't weight could give you quite different results. So often what you have to do is go back and look a little bit at the survey design to see how exactly it was carried out, and then consider whether whatever you're interested in might be related to those variables that on which we based our design, like the unequal selection probabilities and stuff. And sometimes what you can do is even if your sample's big enough, do your analysis within some subsamples where you would expect that the survey design shouldn't have that impact, like, and see if you then get different results. So there are all these different things that are possibilities, which takes time. So now let's go to design-based variance estimation, which is the thing that a lot of people get frustrated by. And as I mentioned before, we've got the complex structure of the population and the sample are going to affect your second-order statistics, like your variance estimates and your confidence intervals and your test statistics. And the design-based approaches can account for that complex structure, but as I said, you need more than your survey weights. So, and I just want to remind, here's that same picture again. your design-based variance is based on what you actually observed and what you could have observed from samples from the same finite population using the same sampling process. So we've got the actual sample we had and the ones we could have obtained, and we're interested, the design-based variability is picking up these differences. So now to do design-based variance estimation, there are two options. One we call the analytic approach, which often people call linearization or Taylor method, or economists like to call it the delta method. And then we've got replication. And so we've got things like the design-based bootstrapping, or we have balanced repeated replication, or we've got jackknifing. There are different things here. Now, for the analytic approach, essentially what you do is you have a formula into which you plug your values. And the formula has to be appropriate to the design that you have, has to be appropriate to the particular quantity you're estimating. It should also take account of any adjustments in the weights that you're doing. And so the drawback is it's often too complicated to come up with a good formula. And what we often have to do is make compromises. Like we'll say, well, the survey design was actually this. We don't have a formula for that, but if we say it's sort of like this, we do have a formula. Or, well, we don't think the weight adjustments had that much effect, so we'll leave those weight adjustments out of the formula. But the analytic approach was one that was used, is the traditional way, and actually it's still in some ways the gold standard in that when we come to replication methods, we often compare the replication result to a correctly done analytic result. And that's often one way that we look at the quality of our replication methods. Well, the replication methods, as you can expect, what we do is you can actually estimate that design-based variance by taking a large number of different subsamples. And we call each of those subsamples a replicate. And with each of them, we estimate the quantity we're interested in. And then we look at the variability amongst those subsample estimates. And again, how you combine those subsample estimates depends on how you picked your replicate samples. So the formula, how you combine them varies. So we had many different possibilities, but at StatCan we decided to go with bootstrapping, design-based bootstrapping, because it did seem to be the most versatile. And I think now you can see that it's on many of the bootstrap weights are on many analytical survey files. But one thing I should mention is we only generally have them there for the confidential survey microdata files. There aren't that many pumps that have the bootstrap weights on it. And the problem is that people discovered that if you looked at the pattern of those weights in those bootstrap replicates, they could determine some characteristics of the sample that were confidential. So even though we actually went to replication thinking it was a method to provide this extra information, we've had to back off. There are some surveys where we can provide it though, like the General Social Survey. You have bootstrap weights on your pumps. And there are some other small situations too. And so we decide on bootstrapping, but we actually pick the bootstrap samples for you. And why we do that is in order to properly do the survey bootstrapping, we have to do weight adjustments as well. And those weight adjustments are quite complex, quite time-consuming. The information for doing them isn't usually on our data file, so we can also include some other complexities there. So we provide the bootstrap samples. The researcher doesn't do his own bootstrapping. So we're now back down to what are we going to use for software for design-based analysis. And as I said earlier, we've got a lot more choices now. Here's some ones that that we have seen people using, and we've looked at them a bit ourselves. Sudan, which doesn't happen to be in that many RDCs. I don't know whether it's in the one here or not. Is Darcy here? Yeah, it's here, Darcy? Okay. You can use it. Stata, and there are various versions of Stata. Actually, from Stata 9 onwards, you can use it. SAS 9.2 survey procedures will allow you to use the bootstrap weights. Another program or software that probably people aren't familiar with, but probably would be useful for a lot of researchers is WestVar, which is a product from WestStat. And then StatCan provides some SAS macros. And the most recent one, I think, is BootVar 3.2 for SAS. Now, something you can see here, I say, in Sudan, if you're using Sudan, you have to specify that your replicates were actually BRR replicates, or Stata 9 and 10, BRR, SAS 9.2, BRR, WestVar. And that's because, actually, StatCan is the only major statistical agency that uses survey bootstrapping for their method of variance estimation. So in order for people to use some of these software packages, we had to look at how they could do it with our bootstrap weights. And what we did is we looked at the way that BRR replicate estimates are brought together, and how they're brought together with our bootstrapping, and there's quite a similarity there. So we can see that you can specify in many of the software that your replicates are BRR, and you'll come out with the right bootstrap variance estimates.
Georgia,
Yes.
I noticed just in the latest version, I don't know if it was the previous version of SPSS, they have a series of commands that are preceded by the letter CS for complex sample. And there's something called CS plan where you define what the complex weights are.
That's something new to me,
It's in version 18.
which has just come out.
Well, it's been out for a little while.
That's interesting, because we actually contacted SPSS back a ways, and they didn't seem to be interested in doing that at all.
I'd be interested in, if you have it, if you can get your hands on it and have a look at it, I'd be interested in knowing
Oh, okay.
whether or not that is possible.
Yeah, okay, this was just a few months ago, and they didn't seem to know what we were talking about, or didn't, if we wanted to pay for the development, they would maybe do it, but they were coming up with high prices, so that would be very interesting to see. Yeah, yeah. So you've got a lot of software packages. They really do vary in what procedures they handle. Actually, Stata is the most extensive in the different procedures that it can carry out. Sudan's a little bit behind that, and then WestVar and say the SAS 9.2 have a smaller number. They all have the key basic ones, but above that it's different. Even if they have particular procedure, they do differ in what estimates they calculate. For example, what diagnostics and test statistics they provide. Even if it's, say, linear regression, some will produce more diagnostics and test statistics than others. Actually, BootVar is the one that doesn't produce very much of anything. You can get your point estimates, but other than a standard error and a confidence interval on each estimate, there's not much else there. Sometimes you're interested in being able to take the output and put it right into a paper. Well, they do vary in the publication quality. And I would say that probably Sudan is one of the worst. It reams and reams of output. And how they do vary is ease of use. So, as I say, you can maybe pick one that's more comfortable than you would have been able to in the past. The WestVar package is actually free from a WestStat website. And it's actually a point-and-click package. So that would be the one that I would recommend to folks who are SPSS users, and they're not comfortable programming. WestVar would be a good option for them to consider. Now, StatCan has had a bootvar version for SPSS, but it's no longer going to be developed or maintained. So there's only going to be the bootvar for SAS. So that's another problem for SPSS users. That's it. Now, something I'll mention though is our little center is just about finished a small document on how to implement bootstrap variance estimation in some of these packages. So we just need a little wee bit more editing, and then it'll be available in the different data centers. So I'm hoping I'll be interested in getting some feedback to see if people find it useful or not, and some suggestions of what else should be in there. And we actually show some examples with all these different packages that we have here. Now, another thing I'll just, this is the last thing I'll do, is people say, well, why can't I use the standard software? Because it'll take a weight statement. And why can't I use that? And maybe I could use a normalized weight. I've heard about that. So unfortunately, it's not a good choice in many situations. But here's one very simple, straightforward choice. Let me see if I can find. Okay. So suppose you actually have the situation where you look as if you have a situation that is appropriate for ordinary linear regression. So we've got y is a linear function of your x's plus an error, and the errors are IID 0 sigma squared. You want to use your weights, so if you put this in, say if you're using SAS, you use SAS proc reg, and put a weight statement, your coefficients would come out to be, now I keep losing my, oh there it is. Here's your coefficient estimate, which looks pretty familiar, where this W here and here is a diagonal matrix with your weights along the diagonal. Now, if that model actually is true, and this is how you estimate your coefficients, then actually an appropriate variance estimate would be something of this form, which has this x prime wx bread, like a sandwich at each end, inverted, and then you've got something in the middle. And that would be an appropriate variance estimate. And you can see here that because we've got the weight matrix twice in something that's an invert, and twice here where it's not inverted, whether or not you normalized your weights isn't going to affect things, because that weight normalization constant just drops out. So this would be nice what you do. But most standard software would go and estimate your variance like this. And this, you can see, would be very much affected by whether or not you had done an adjustment here. And really, this variance estimate is only appropriate if what your weight is a frequency weight, telling how many sample observations you have that are exactly the same. And it's not assuming that it's a survey weight at all, which has a different meaning. So your variance estimate would be quite wrong. Now, if you actually used a normalized weight, it would probably come to be closer to this particular quantity. But it really isn't appropriate. Most software, this is what you're going to get. I think in Stata, if you use the robust option, you may be able to get this as well. But for most standard software, this is what you're getting, which really isn't appropriate. If you actually went to design-based software, you'd estimate the quantity something like this. Again, you have your same, your bread at the end of each sandwich is different, or is the same as the others, but the middle part is different. And this particular estimate has good properties even when your assumed model error structure is wrong. So it's another case of why we would recommend that you go to a design-based if you're not sure that you know what your error structure is. Okay, I'm just going to take 2 secs. Here are a couple of situations where we've got weighted and unweighted estimates. And so this one is actually from a 1988 survey in the States. And this came out of a paper by Korn and Graubard, who were looking at why should you wait, or what if you don't wait? And what they were interested in here was the percentage of maternal smokers for 2 different education classes. So they had 2 different levels of education: mother's education less than 12 years and 12 years. They actually had a third one, but I left that out for now. Percentages using your weights and not, plus or minus the standard error. So for mother's education less than 12 years, weighted estimate of the percentage was 31.5, unweighted was 32.8. Not that much different. But when we go to 12 years of education, weighted is 37.3 and unweighted is 33.2. A much bigger difference, and those differences are quite large as compared to the levels of the standard error. So these are quite different. And they explained that why you were getting differences between the weighted and unweighted was because of their sampling, different sampling fractions from the black population in the States as compared to the white population. So you really, really needed to use your weights when you did any estimation. And I think probably that difference would convince people that you should. But here's another little situation. This is data from the Canadian Health Services Access Survey. I forget which one. And here I'm the one that should be saying which year this came from. And that access survey is really interested in how people feel they have access and whether they're satisfied with the treatment they receive from our medical system. So suppose we're interested again in a proportion. And we'll look at the proportion of people with a regular doctor who believe that they receive excellent care. And what we want to do is compare results for Ontario and Alberta. So here we're going to use 3 different methods to carry out our analysis. We're going to do no weighting, and then the classical standard error that you'd get out of SAS or SPSS. Normalized weighting, and we could call it the classical standard error. It's what the software provides if you put a weight in, normalized weight. And then we'll use weighting and we'll use a design-based standard error. So let's look at Ontario, the estimate itself. Actually, no weighting and weighting, the percentages don't change that much. Also in Alberta, weighting, no weighting or weighting, very little difference in the estimate. Often when people are new to survey data, they'll say, okay, I don't have any differences in whether I weight or not weight. I can just use unweighted analysis, and they'll go on like that. But something they really need to look at are the standard errors. Here again, I'm losing. Okay, so for Ontario, actually, no weighting with the classical standard error, or this normalized weighting where we've got the classical standard error where the weights are considered to be frequencies. Standard errors were practically the same. But if we did a design-based variance estimation, standard error went way up. And we see the same thing happening with Alberta. So if we look at the difference in these percentages, which is what we were interested in, it's 4.7 if there's no weighting, 4.4 if we weight, whether it's normalized or not. But where the major differences are in the standard errors. Here, 1.83, here, 2.67. So most people would just do a little t-test. They take the difference, this difference divided by the standard error, and here are the values of the t-statistic, 2.56, 2.40, and 1.65. If you looked at the p-values, it would be 0.01, 0.02, and if you use weighting and design-based standard error, 0.10. So using either of these two methods, we would have come to the conclusion that the provinces seem to differ in the proportion of people that are happy with their doctor. Well, taking a design-based approach, if a 0.05 was our cut point, we would come to a different conclusion. So it's just a case of, this is a situation where you cannot decide that you can do away with the weighting and the other parts of the design just based on what the point estimates are. Yeah, Kathy?
Is it systematically the case that design-based weighting will always increase your standard error?
No, not always. Frequently, it's more frequent, but we have to remember these are all estimates, so they have error in them as well. And it could depend on the survey design and what you're studying. For example, if it happened to be something where stratification was efficient, and stratification often reduces your standard error rather than increases it, and if what you're studying didn't seem to have any intra-cluster correlation, it could be that accounting for your weights, accounting for the survey design would reduce your standard error. But most cases we find it increases it.
Which is the strongest argument for
Yeah,
doing it.
yeah. The number of situations where it's going to change your conclusions, well, I don't know. It could. I'm going to stop there. I just put here at the end 3 or 4 books that if people want to do some more reading, they're all interesting. If you're studying health data, the analysis of health surveys is a actually of the 4 books, that would be the one I'd probably read because it just doesn't apply to health surveys. Lots of practical information, but these are ones, and I just gave my contact information on the back. So I went way over an hour.
That's great. Thank you, Georgia.
Yeah. Any questions?
You want to get back to the question I asked?
Yep. Okay. What slide was that? It's way back near the first.
Keep going.
We're going to get that one? No, actually I want to go back to SLID. You were interested in SLID. My goodness. Okay, here. Now you were saying, okay, a lot of things.
Let's say somebody is going to do analysis, and given the way that their target population is defined, there weren't enough cases in panel 1, but if you combine panels 1 and 2, there would be enough cases.
Okay.
So
Okay.
they would do their analysis between 96 and 98, pooling panels 1 and 2.
Yeah. Oh, okay. Now, actually, if that was the time period you were interested in, StatCan has already done that for you. Where 2 surveys overlap, those 3 years, they have actually created another. behind the scenes, there actually is another longitudinal file that uses data from those 2 panels for those 2 years. And they presume the target, they've adjusted the weights so that the target population is as close as possible to being the population in 1996 for this combination with this combination. As best, the adjustment as best they can. And then they'll have another small longitudinal file, which is for these 3 years. And then another longitudinal file that's for these 3 years. But a lot of people are actually interested in some longitudinal thing that actually is over a 4-year period. And they would like to combine 4 years here and 4 years here. And that's possible too. But what we usually talk about here is pooling of different files. And really what we want you to do is think of could you actually create a larger finite population that consisted of the people in 93 and the people in 96. And when you fit a model to them, put some variables in your model to identify from which target population the people came, to see if it matters. Because particularly with SLID, this is economic data, so you have your economic cycle going on. So you could be at a different part of the cycle in these 4 years than you were in these 4 years. So,
So you could do sort of like a pseudo-cohort.
yeah, and actually check on it. Do some diagnostic work as to whether it seems appropriate to pool those 2 together. Yeah. Okay.
I have this vague memory of when you're doing this kind of pooling, which you make a choice between allowing the survey weights to sum to 1 within a survey.
Yeah.
And then you're, like when you're, the groups that you're pooling, and that way you're allowing each group to
Yeah.
have the same weight, or you can just renormalize the whole thing to sum to 1.
You could. I mean, if you were but it depends.
But you're right. I mean, if you're trying to like incorporate something about like but you can still control for where they came from.
Yeah, but sometimes if you look at what you're estimating, it seems reasonable just to leave the weights as you have from the 2. So the sum of the weights then would add up to the population from the first survey plus the population from the second survey. And often that doesn't matter because most times you're not interested in estimating totals. You're estimating relationships. So sometimes people will say, okay, I'm going to adjust the weights so that they seem to reflect the population at the time of the second survey or whatever. And they do that, but many cases, I think it's more, you can just put them together, but do a lot of diagnostic work to see whether you really can make assumptions that the same relationships are holding in your 2 populations. Yeah.